So good morning, everyone. So like we were talking about last night, yesterday, we were looking at what the geometric optics says, and we say that the power flowing through a given transported in a tube of rays does not change, and it remains constant, especially if the material is a lossless medium, so to speak. And we saw that the areas through which the power is passing, their ratios are equal to the ratios square of the amplitudes of the electric field intensities at those positions. So today we'll look at, we say that the ratio of A, that is A1 by A to A2, should be equal to the ratio of the square of their distances, because for spherical surfaces, A1 would be something like 4 pi R1 squared, and the other one would be 4 pi R2 squared, and therefore you can see that their ratios are going to be the square of their radii of curvature. And therefore, we can simply write that ratio as R squared, that is the position of A1 from the primary source, over the position of A2 from the primary source, all squared. And therefore, we can get a value for E1, for E2, or the modulus of E2 with respect to, or relative to E1, and it will be given by the ratios of those radii themselves. Now, if we account for the propagation factor, which is the exponent of minus jk multiplied by the direction or the distance traveled, then we would see that we can always write this as R over R plus R E1 modulus and the exponent of minus jk and R plus R, which is the position where we are measuring R2, that is the observation point. And if we can always extract the big R, and we see that this one is exactly the field, including the phase propagation factor at the position of A1. And therefore, we can write it straight away as R over R plus big R, given multiplied by the field at the position of A1 and multiplied by the propagation constant beyond the position of A1. So we can write this relative to the, we can use the position of A1 as the reference point now when we look at this. So in general, the wavefronts will not be spherical. Okay? And the spherical is just an idealization, so to speak. And therefore, what we want to look at is to try and see what would happen if we have curved reflecting surfaces with an equal radii of curvature in the xy and the xz planes as shown here. That is, the curvature on that plane is different from this curvature here. And this is what you are going to meet, especially when you are dealing with antennas or reflector antennas. I'm sure you guys have seen the satellite dishes, especially the ones we have on top of American wing, or even the ones you'll see along the buildings for communication with Safaricom or Telcom and so forth. So this is a reflector or a reflecting surface that is curved both in the XY and the XZ direction. Now we are going to look at 4 rays, okay, striking the reflector at these angles. And we expect that because the curvature, they are curved, the reflected wave will be, say for example, the ray 1 will be reflected, will hit the reflector and get reflected down. Then A2, let's say the ray 2 will be hitting that and then get reflected, and it will go to a point Q2, not necessarily Q1. Ray 3 will be reflected and comes through Q prime, while ray 4, which is a blue-gray, will go and pass through P prime and Q. So what we are saying is that the reflected waves do not necessarily cross at the same point. That is, they do not focus to the same point. And this is what we call astigmatism. Okay? Where if you wear specs like I do, if you have an eyeball that is elongated, what happens is that most of the time you'll not be focusing at the same position, and therefore you start seeing double, so to speak. And this is what would happen. So the lines connecting Q prime and P prime and Q, where the two rays focus, and the P and P prime are usually referred to as caustic lines, or caustics in simple terms. So the tube of rays incident on the curved surface is defined by the rays 1, 2, 3, and 4, and we are going to assume that they are all parallel to the x-axis. And after reflection at the curved surface, the rays 1 and 2 will focus at P, rays 3 and 4 focus at P prime, ray 1 and 3 focus at Q prime, and ray 2 and 4 focus at Q. And the tube of rays is therefore said to be astigmatic because the point of focus is not the same. If the curvature, or if the curve was truly parabolic or spherical, most of those would focus at the same position, okay, at the same focal point, and therefore would not have astigmatism. But the astigmatism is coming because of the difference in the curvature of the surface. The lines P prime and Q prime are what we have said are called the caustics, or the caustic lines. Now, we are going to consider an astigmatic tube of rays along two wavefronts of areas A1 and A2 as we have there. That is, the rays are moving, and we have the caustic lines and those positions. So that is the area A2 and the area A1, with the radius of curvature for A2 given by R2 plus R, and the area of curvature, or the radius of curvature of A1 given by R2, so to speak, or R1, so to speak. So the ratio of the curved surfaces is then given by A1 by A2 equal to R1 multiplied by R2 over R1 plus R and R2 plus R. This can be seen because all we are saying is that we can look at the angle subtended at the caustic line on that level, okay? That angle and the angle of connecting, which is parallel to the XZ plane, so to speak, that is subtended at those positions there. So we can always get the values properly using that kind of curvature. So when R is greater than 0, then E2 will be given by the square root of R1, R2, or R1 multiplied by the field at the position of A1. So whenever R, or the minus of R1, R2 is less than R and less than 0, then we'll add a minus 90 degrees phase term to the field factor, and we add 180 degrees if that value is actually greater than minus R, or when that condition is satisfied. So geometric optics will not be useful if we have that the R itself is at minus R1 or R minus equal to minus R2. That is at the caustic lines, where the caustic lines are located. If we are at that point, then we cannot be able to use geometric optics to analyze the problem. So for cylindrical curved surfaces, such as, say, you take a cylinder and cut it through, or a hollow tube and cut it through the axis, you'll get a cylindrical curved surface with one side that is parallel to the z-axis having a radius of curvature that is infinite. This would be the usual cases, especially when you are making a reflector for an antenna. And therefore, we can put that R1 is equal to infinity, and E2 is therefore going to be given by that simple equation there. So the general geometric optics expression for the field is therefore going to be given by a reference field multiplied by a factor which we call a spatial factor f of r and the phase propagation constant for the field, where therefore you can say that E is the electric field intensity at the position of r, E naught is the amplitude of the electric field intensity at r equal to 0 or r equal to r naught, which is the reference point. Phi naught is the phase of the field intensity at the reference point, not necessarily r equal to 0, and Fr is a spatial attenuation factor. Okay, so r will be the distance from the reference point. So the exponent of minus jkr is of course the phase propagation factor, with k carrying its usual meaning of 2 pi divided by lambda or omega divided by c. And therefore, the field at a position r would be given by a reference field multiplied by an attenuation factor and multiplied by a phase propagation factor. This is what you get in geometric optics. Now, we look at what happens when we are having a conducting strip that is scattering the electromagnetic wave. Say, for example, this would happen especially for those of us who would be working with the military and you're trying to detect a radar, an object using the radar system. So we consider a line source that is illuminating a perfectly conducting strip of finite length, L, which is assumed to be much greater than the wavelength of the illuminating radiation. Okay? And it is illuminated at a distance d from the source. We can model the situation as shown below. That is, this is the line source, and then we can place a cylindrical surface about centered at the line source, and then we can see that the angle from the line source to the end of the strip, which is of length L, is theta naught, and the radius is just r to that point and to that point. So Q is at the surface that we have, the cylindrical surface of the wavefront that is being reflected from the strip. We can therefore remove the conducting strip by using the image, virtual image sources theorem, where we assume that the reflected wave going to the position of P, where P is the field point, could be taken as coming from behind the reflector at that position minus D, okay, or D behind the reflector itself. And we can always now compute the values of that. We are going to assume that P is sufficiently far away such that all the rays coming from every point on the conducting strip can be assumed to be parallel. So the direct and reflected rays are then essentially parallel at the field point, and the geometric optics may hence be applied to estimate the electric field intensity at the field point. So the direct field is given by ED equal to R over R plus R naught and multiplied by E1 exponent of minus JK R naught, where R naught is the distance measured from the cylindrical wavefront at Q. From geometric optics, the reference amplitude E naught at the center of the strip will be related to E1 as E naught squared multiplied by A naught equal to E1 squared multiplied by A1. And where the cylindrical wavefronts originating from a line source, okay, of a length L will have an A1 and A naught given by the length of the line, okay, of the strip multiplied by the distance D, and A1 would be L multiplied by R. And therefore, E1 is just D by R multiplied by the amplitude at E naught. So when E naught is equal to E naught exponent of JKR, then ED will be given by that expression as we have there. So the R will be given as R naught plus big R plus the small distance d, the cosine of theta, okay, which is in relation to the center of the strip itself. So if R naught is much greater than the radius of curvature of the wavefront, then R plus R naught is approximately R, and we can therefore write that as simply that equation there. And this is what we were looking at before, and this is what we call the cylindrical wave, because the E field, instead of varying as a function of R, of 1 over R, it's varying as a function of 1 by square root of the distance. Therefore, the power flowing will be proportional to 1 over R rather than 1 over R squared as in spherical waves. And this expression will hold for all theta except in the shadow of the strip. That is, for the angles minus pi minus theta naught, less than theta and less than pi minus theta naught. Where theta naught is, of course, as shown in the diagram, is the arctangent of L, the length of the strip divided by twice the distance, okay, the distance from the line source. So values of theta that are outside this range will be corresponding to the regions behind the strip, and the direct wave ED is going to be 0 in these regions. So the cylindrical wavefront that is passing through Q will also be passing through Q prime, where Q prime is at this conducting strip. And the reflected ray can therefore be regarded as coming from an image line source of that is 180 degrees out of phase with the actual line source, because we say that the electric field intensity must be 0, or the tangential component of the electric field intensity must be 0 at a conducting surface, and therefore the line source must be changed in phase so that it's the negative, so that the fields from the image source and the actual source cancel out at the position of the conducting strip. So this, you can see it from here. This is the Q prime we are talking about, and we are saying that this should be the negative of that, so that the field at that point becomes, the tangential field becomes 0 at that point. And therefore the reflected wave, or the reflected wave, the field will be given by just the minus of what we had before for the angles minus theta naught, less than theta, and less than theta naught. And for theta, for the angle of theta greater than theta naught, then ER is just going to be equal to 0. So the total geometric optics field is then given by the direct field, that is the direct field coming from the line source, plus the reflected field that is reflected at the conducting surface. And what we see is just going to be a sinusoidal value propagated with it will have an uniform amplitude that is sinusoidal with relation to the distance of the line source from the conducting plane, and multiplied by the phase propagation constant finally. So the interaction between electromagnetic field and a material body is essentially a local phenomenon, as long as the body is not very small when compared to the wavelength. And therefore, geometric optics can be used to estimate the contributions to the fields that are set up by the interactions. But the estimate will require additional terms that come from what we call edge diffraction. That is when the field is, or the ray is, or the radiation is attacking the object on the edges, there will be diffraction at those edges. And another type, which is called a creeping wave diffraction. So creeping wave diffraction will explain the mechanism by which the energy is diffracted into the shadow region of a curved metallic surface, e.g. a cylinder. So for example, if you are illuminating a cylinder, the light may fall over the other side. This is important, especially when you are trying to do things like photolithography. So we consider edge diffraction in this particular course, and just for simplicity. And the law of edge diffraction states that in a homogeneous medium, the diffracted ray and the corresponding incident ray make equal angles with the edge at the point of diffraction and must lie on opposite sides of the plane that is normal to the edge at that point. So diffraction of a wave that is incident on a conducting edge and its normal incidence and at oblique angles is shown here. That is, for an oblique angle, we have that the diffracted rays are on the same side, okay, they lie on the plane, and we have some kind of a cone, so to speak. For the normal incidence, we have that kind of value there. This does not mean that it's going into the conductor itself. Of course, the fields in the conductor must go to 0. So the diffracted field, ED, from the conducting half plane can be expressed as ED equal to D E1 over root R and the exponent of J phi. This conducting strip, the one we looked at when we were introducing diffraction, is what we are looking at now to see how the geometric field and geometric optics and the physical optics come about, or how they compare. So D will be called a diffraction coefficient, and it's usually given as in meters per square root meter, or the square root of length. E1 is, of course, the amplitude of the incident wave field at the reference point. Phi is the phase of the incident field at that reference point, and R is the distance from the edge. So K, of course, carries the usual meaning, and therefore when KR is large, the diffraction coefficient of the plane wave incident normally on the edges is given by that equation there, where we have the secant of theta minus alpha, and we shall define what these alphas and thetas are in a diagram, so to say. So the addition, the addition here is used when E is parallel to the edge, and subtraction is used when edge is parallel to that edge. So the angles theta and phi are defined as shown here. That is, our incident ray is coming down, and we are measuring theta relative to the plane that contains the edge, and the theta is that the angle between that plane and the diffracted ray itself. So this is a little bit different from how we measure the normal incidence and so forth when we are dealing with refraction and diffraction and reflection, so to speak. So the equation of D will not be valid near the shadow boundaries, however, that is for thetas that are greater than the theta nodes that we were talking about. So for the diffraction field, the conducting surface or the conducting strip will be illuminated by that line source, and you have seen that these are the theta nodes we are talking about, and these are the ways the angles are. So we have edge 1 and edge 2 there, and therefore the thetas and the alphas will be defined in terms of those. We are going to give them the subscript, so to speak. So, and the ED is therefore the diffracted or the direct field is given by that equation, and where D1 and D2 are the diffraction coefficients are the associated edges 1 and 2, and R is that, and the amplitude is of course given by that value at the edges. And so from the geometry of the diagram, we can see that R1 is going to be given by that equation, R2 is given by that equation, and E1 is going to be given by that equation. And the angles are, of course, therefore defined as shown at the edges 1 and 2. And therefore, D1 can be expressed as that, and D2 expressed as that. So we'll go quickly over this so that we don't have to, this I'm giving as a matter of completeness, but we don't have to remember the expressions themselves. So whenever R is much greater than this strip length, then R, the square root of R1 is approximately the square root of R2, and it is therefore approximately the root of R. And therefore we can write the fields as shown there, where this, the CSC is of course the cosecant, and we can say that this expression will be accurate for all theta except near the shadow boundaries. And at the shadow boundaries, the field will be half the value obtained from the power given by the geometric optics in the absence of set strip. And thus the total field will always be given as E, given by the field from the geometric optics and the field from the diffraction theory. And this will be illustrated as shown, where L is about 10 lambda, and therefore making L much greater than lambda, and D is just a quarter wavelength. That is, the illuminating source is only a quarter wavelength from the conducting strip. And this is what you'll get. So the direct field is given by that. The direct plus the reflected will be constructively, destructively adding together, and then goes down, and then comes up like that at the edges. And the geometric field will be given by that value there. That is, geometric field means that at the boundary or at the strip, we'll get a sharp shadow, so to speak. So that's when you are trying to work with PCBs, you've been told that whenever you are exposing your circuit to the PCB surface, you are supposed to make sure that the printed side of your transparent paper should be lying on the PCB itself, so that any diffraction that would appear because of the light passing through the thickness of your paper does not blur the edges of your circuit, and therefore you'll get the dimensions correctly. This is something you have to always remember, that diffraction is a real phenomenon, so to speak. So that's what we have to say for diffraction. I know that diffraction has had a few heavy mathematics, but I've just rushed through because I don't usually expect that we'll have to, to work through that kind of whatever equations in a class or in the exam, environment, so to speak. These are given as a completeness, but doesn't mean that it's not important. You should try to read and understand what diffraction is all about. You are going to meet it in the field as you work. Any question? Now we need to look at what we call the dielectrics. And by dielectrics, what we are trying to say is that we are trying to look at them in terms of insulators for the people who will be working with high voltage engineering, that is power systems, transmissions, and base station, substation designs, and so forth. You need to know how the high voltages will react with, with the environment and also with the materials that you're going to use. In this part of the course, that is the first semester course, we are required to look at gaseous state insulators. The solid state insulators will be looked at in the second semester course, that is 452. Now, how I'm going to introduce this, I'll introduce this in a bit of a roundabout way. We'll first of all look at how the fields interact with matter, because at the end of it all, we've just been dealing with the fields, but we don't know how they really work or how they interact with matter at all. We have just been looking at the fields, and most of the time we've just been saying a dielectric of this nature and a dielectric of that nature. So, but what happens when you have material in between? So to attack this value, what we are going to look at is the fields and matter interaction. But this is just an introduction. Then we'll just fly through the gaseous, insulators after we have seen how these interactions come about. Now, for us to deal with this, we have to look at, most of the time, we are dealing with charged particles. And these charged particles how do they behave when we apply an external force, say m? So let V be the velocity of a particle of mass m under the influence of an external force F. F can be a mechanical force, it can be an electric force, it could be all sorts of forces. But how will that charged particle behave? So from Newton's second law of motion, we know that force F is equal to the mass of the particle times its acceleration. And therefore, we are assuming that its mass could be changing with time, and its velocity should also be changing with time. And therefore, the Newton's second law of motion will be mathematically expressed as F is equal to d dt of m multiplied by v. That is the change in particle momentum. Now, if r is the position vector of the particle in space and is changing with time, then the velocity is just given by d dt of r, and under an relativistic motion, m is going to be equal to a constant. We know that as the velocity approaches the speed of light in free space, we'll expect that the mass will increase using what we call the Lorentz transformations, and the particle mass would look like it's going towards infinity, so that we don't violate Einstein's postulates that no particle of finite mass can travel at a speed greater than the speed of light. Okay, so for this particular case, for our cases, the V's are going to be very much smaller than C, and therefore we can say that m is going to be a constant, and therefore Newton's second law of motion just becomes m equal to d dt or d dt of r, and you see that is the second derivative of the position vector of the particle as time progresses. So F, like we said, could be either an electric coming from an electric origin, it could be a magnetic origin, or gravitational, or even mechanical. So it is through the external force F that the external world will interact with the particle. And this is the condition, it comes from the equation of Lorentz, the one we were talking about, E plus V cross P and so forth. So the acceleration would be the response of the particle to the external force F. And in the Cartesian coordinate system, the vector quantities can be expressed in terms of their components as F equals to the x component of F plus that, and the V will be given as that. And hence, the velocity V is going to be given by d dt of x cap x, y cap y, plus z cap z. And this comes out very easily as dx dt, which we recognize as the x component of the velocity, and dy dt, the y component of v, and dz dt, the z component of v. And so that we can have that equation there. So, and F will also be given by the Newton's second law of motion, where we are using a constant mass, and we are taking the derivative of v, and we get it as given as the second derivative of the components of the position vector. So the particle orbit will then can therefore be obtained from two successive integrations of the force F. That is, we'll integrate the force, and then we can get where, or the locus of the particle as time progresses. Where will it be in space? So in a general curvilinear coordinate system, we know that the basis unit vectors will not be independent of direction. Say, for example, for a cylindrical coordinate system, the basis unit vectors are the radial vector r cap and the azimuthal angle vector phi cap, and of course the z, or the axial vector, unit vector z cap. Okay, where we assume that the axis of the cylinder is lined along the z-axis. And we see that r cap changes direction as we go around the cylindrical curve. And therefore, when we start dealing with the derivatives, we must also worry about the derivatives of the unit vectors themselves. So in the cylindrical coordinate system, we have that f is going to be given by r cap f of r plus phi cap f of phi plus z cap f of z. And v will be given by those equations there, where the position vector, which I'm using a big R to differentiate it from the small r of the radius of the cylinder, will be given by r cap r plus z cap z. So the r, the radial vector in the cylindrical coordinate system, and therefore we can use this transformation matrix to get from the x coordinate, the Cartesian coordinate system, to the cylindrical coordinate system using that value there. So if f is defined in the Cartesian coordinate system, then f of r is just going to be the x, the coordinate, the Cartesian coordinate system definition for f dot the basis vector in the cylindrical system, and that also follows suit. And therefore v is going to be given by the time derivative of the position vector r, and you can see that is going to be given by that value. So when we have that, we see that now in this case, v has the normal radial component of the velocity, and another velocity that is varying, or another term that is arising from the derivative or the time change of the basis vector r cap. Okay, and that one is just like in the Cartesian coordinate system. So d dt of r cap is going to be given by, it can be expressed as, using the chain rule, we can always say it's the derivative of r cap with respect to r multiplied by the derivative of r with respect to t, that is the radius, so to speak, plus the derivative with respect to the angle, azimuthal angle, and its derivative there, and so forth. So, and since r cap has a fixed direction as r and z changes, that is, it doesn't change, this term here can be set to 0, and we can see that the d dt of r cap is just going to be given by d d phi of r cap multiplied by d phi dt. If you see this is the rate of change of the angle around the circle, and therefore this is what we usually call omega, or the radian frequency of the radian velocity. Okay, so consider this equation here. We are looking at, we are changing, and this is the change in the position vector delta r cap, and we see that it's going to be given by delta, the phi, the unit vector in the azimuthal angle, multiplied by the value of delta phi, where delta phi is the angle subtended by this small arc that is passing through there as r changes to a different value r and r delta r cap. So then we can see that d phi of r cap is going to be the limit as we take the delta phi going to 0 of delta r cap over delta phi, and this gives us the value of phi cap. And here we have shown where the delta phi R cap is shown in the diagram. And therefore, ddt of R cap is just that value, phi cap multiplied by d phi dt, and we can write it as phi cap multiplied by omega, where omega is just that value there, the time rate of change of the angular velocity. So the velocity vector is therefore given by that equation there, that is the radial component, plus a component that is circular there, plus an angular component, and that is the axis, the axial component. The acceleration will also be given by the derivative of that with respect to r, and we can see that that will also be given by that big equation there, because everything here is changing with time. And when we look at that value, you can see that the azimuthal angle itself is defined as that, and therefore we can always get a value for the delta phi's to get the unit vectors. And therefore, we can see that dgt of the phi cap is going to be given by that equation, where the dd phi of phi cap is expressed as that, and we can see that it's just the minus of r cap. So the time rate of change of phi is therefore given by minus r cap d phi dt, and we see it's just the omega we had before, or d phi divided by r. So d dt of v cap of the velocity therefore going to be given by that expression, and we see that now we have new components compared to the Cartesian coordinate system. So in terms of spatial coordinates, then we can write these values in terms of the r's and so forth, and we see, and we can therefore write the velocity or the acceleration as given in terms of r and whatever, and the r's. And this is what we have for this particular case. So the force in the cylindrical coordinate system is therefore going to be given by m multiplied by that equation that we have obtained for the acceleration. Is given by that. And this can be shown, that is, we can always take some terms from this end and put them to the other side, which are not derivatives, and put them to the other side, so that we are left with just the derivatives on one side. And this is what we have done here. Put that value to the other side, and we see that because of the circular motion, we are having an extra force term adding to the applied term, the applied field there. And this is very important to note. So F is going to be given by that equation, and or in other words, we can always write it as F plus that minus an azimuthal kind of component there multiplied by the velocity in the radial direction will be given by those derivatives. So what we note is that the right hand side, that is the product of the mass particle, or the particle mass, and the acceleration that would be measured in a reference frame rotating with the particle at an angular velocity omega. That is, we are sitting with the particle and we are moving around with it, and therefore this is the force that would measure for that particular particle. That's the force that the particle is experiencing. The left hand side, this hand side, is therefore the force that would be acting on the particle as we would measure, as it would be measured in the rotating frame. So the force components are m omega squared r and minus phi cap m omega vr are not external, but they are just because of the rotary motion of that particle. And although they are usually referred to as fictitious, the forces are actual real values. Okay? One, the first term here is what you met in mechanical engineering. It's a centrifugal force that is directed radially outward from the axis of rotation. That is, if you are holding a piece of string or a stone tied to a string and you swirl the stone, there will be a force trying to pull the stone towards the center of the rotation, and another one that is going out is usually from the Newton second third law of motion, that is reaction and action, that tries to keep the stone in a constant orbit around the rotation. Okay, so it's called a centrifugal force, and it's usually called a fictitious force because it really does not exist. It's the centrifugal force that balances the centripetal force on the stone. This equation here, or this term, is what is called the Coriolis force. That is, if you are sitting on if you are walking around a disk that is, you start from the center of a disk that is rotating and you are walking outward, you would feel a force that will tend to pull you backward towards the center. And if you are walking inwards, you will be feeling a force that is trying to pull you outward, so to speak. So, and this Coriolis force, for especially of those of us who will be dealing with military work, is usually a real value, because when you are correcting, even when you are planning to be a sharpshooter or sniper or whatever like that, you need to worry about the force. The Earth is rotating, and therefore the Coriolis force can also affect your aim, so to speak. And it's different in different directions in the northern hemisphere and in the southern hemisphere. And is the reason why we have winds that rotate in different directions, when depending on which side of the globe you are on in relation to the equator. So, an angular acceleration on a particle with an inward velocity component of minus VR, and an angular deceleration to a particle with an outward velocity of plus r. So, Coriolis force is used by figure skaters. I don't know whether you know what skaters are. If you go to the ice rink at Panari, I think, and you rotate, if you pull your hands together close to your body, your speed would increase. And when you pull them out, you'll get them, whatever your speed will start to reduce, so to speak. And this can also be used by those people who churn milk to make butter or cheese and so forth, okay, by rotating the milk or spinning the milk in a reservoir, so to speak. So the spin is decelerating by outstretching the arms away from the body again. So the equation of motion therefore states that the time rate of change of the momentum is proportional to the applied force. So for the phi component, if we multiply the force equation by r, we'll get something like r phi f of phi equal to d dt of omega m omega r squared. And what you see is that this r multiplied by force is a torque. Okay, so that is the time rate of change of angular momentum is equal to the applied torque to that value. So the principal forces that will be acting on a charged particle of mass m are electrical and magnetic mostly. So the electric force will be proportional to the electric field intensity. The magnetic force will be proportional to the magnetic flux density. And therefore F is just going to be given by md dt of V cap equal to Q into E plus V cross B. And this is the equation that we called the Lorentz force law. So in the cylindrical coordinate systems, then we can expand V cross B as follows. That is the R cap, phi cap, and Z cap. The R component or the radial component, the azimuthal component, and the Z component, and the B's are the same. And we take that as a modulus. So then we can always say R cap V phi BZ minus VZ B phi and so forth, just like we do the curl equations that we've been dealing with in Maxwell's equations. And therefore, this can be expanded as that. And the expression is then substituted in the equation of motion for the particle to obtain the complete equation of motion, okay, relating the forces. Two situations will be of interest to us. One, the charge particle density is very low, such that the applied field E and B is essentially unaffected by the presence of the charged particles. Okay. Two, then the F acting on the particles will be a known function, and two successive integrations will yield particle velocity and position as functions of time. If we eliminate the time from the position relations, we'll give a description of how the orbit of the charged particle is going through. So a charged particle density, if the charged particle density is sufficiently high to significantly modify the applied field, then the solution of the equation of motion for the particle will require that we also consider Maxwell's equations. So work must be done whenever, okay, whenever a charged particle is moved in space, when we have an external field. And therefore, let F be acting on a charged particle, okay, as the particle is moved from a point 1 to point 2 in space. So the work done against the force is therefore going to be given by U with from 1 to 2 will be given by the integral from 1 to 2 of F dot dl, where dl is the element of path along the integration path. In other words, we can always replace the value of F by its value, that is dv dt multiplied by m dot dl. And this, you can see that dl by dt is of course the velocity again. Okay, is an element of velocity. Or we can therefore write that v dot dv, and we can get this value being given as the value of d v dot v point. I think this one there is a d missing here. Dv dot dv. It's just dv dot dv because that is also dot dv, so to speak. So we can therefore write that u1 and 2 is the same as the derivative of m by 2, the derivative of v squared, and we see that m by 2 v2 and v2 squared minus v1 squared. That is, the work done on the charge is equal to the change in kinetic energy of the particle, or the increase to the kinetic energy of the particle. Okay. So the Lorentz force equation, we have that work is going to be given by the force dot dl, and we can see that this is going to be q e dot dl plus q v cross b dot dl. And what we notice is that v cross b dot dl will be the same as dl dot v cross b, and this we can see that it's just going to be dl cross v cap dot b, and this must be equal to 0 because these two will be orthogonal to each other. Okay, because dl and dv are in the same direction, then we can always find that this equation goes to 0, and therefore we see that a charged particle in the field will just be only the electric field will change its work. Okay, will do work on it, so to speak. So we can see that the work done will just be only responsible, attributed to the magnetic field intensity, or the electric field intensity, so to speak. And therefore, you can say that work done is entirely against the electric field. So it means that if we applied a magnetic field, we won't be changing the value of the, we won't be doing any work on the charge itself, although we'll be changing its direction of motion. So in many cases of interest, the electric field will either be static or will be only slowly varying slowly with time, such that the magnetic effects can be neglected. That is, the charge itself is able to follow the variation of the magnetic or the electromagnetic field. So under these conditions, the electric field may be expressed as the gradient of a scalar potential function, just like we said before for the TEM waves, where we say that E could be written as the minus of the gradient of phi, where phi is a scalar electric potential function. And therefore, we can write that U1 or 2 or the work done is just going to be given by the change in the potential or the potential difference between the position 1 and position 2 respectively. So work done is proportional to the difference between the potentials at positions 1 and 2. And when we combine this with the kinetic energy, we obtain the following equation, that the change in the kinetic energy of the particle is equal to that electromagnetic change or the electrostatic energy of the particle there. And therefore, we say in terms of this as the increase in kinetic energy of the particle as it moves from point 1 to point 2 will be proportional to the potential difference between the two positions. So, how do charged particles move in magnetic fields? We consider a charged particle that is moving in a magnetic field B that is assumed to be directed along the z-axis with a constant phi-directed angular velocity. That is, the particle is moving around with an angular velocity omega, so to speak, that is constant. The equation of motion will therefore be only have a phi component, and it will be given by Q equal to V phi Bz plus M omega squared and R, and this must be equal to 0. So this is what is called the statement of the radial force condition for uniform circular motion. So the rotation is at a fixed angular velocity omega c, called the cyclotron frequency, and this is usually useful for when you are designing cyclotrons in nuclear research. Cyclotrons are things that are used to accelerate charged particles, such as the Large Hadron Collider in Switzerland or somewhere like that. Okay, when you are trying to study particles or nuclear particles. So we have that the cyclotron frequency is given by the minus of Q Bz by M, where this is coming from the radial velocity or the radial force condition equation that we have here. So the radius of the circular path of particle motion is constant because the angular velocity is constant. And suppose the charged particle of the mass m is moving in the x direction with a linear velocity v naught equal to x v naught in a uniform, steady, and crossed fields E equal to Ey and B equal to Bz. That is, we have an E field and a B field in the same space, that is an electromagnetic field, where B is coming out in the z direction and E is pointing in the y direction. So this is a linear polarized wave that we are talking about, or electromagnetic field we are dealing with. And this particle is moving in the x direction with an initial linear velocity of v naught. So how will this particle move, or how will it behave in this region, in the region of the field? So we can assume that the charge on the particle is just the electronic charge, and it's assumed to be positive so that it makes our life easy. And the particle is at the origin of the coordinate system at t equal to 0. That is, we start our clock from time t equal to 0 when the particle is at the position 0, 0 in the coordinate system. So in Cartesian coordinates, we can write that the force will be given by that force equation, where we have both the that force in the x direction plus another force in the y direction. Okay, remember this is what we were talking about when we were looking at Hall effect, so to speak. So we recall that the cyclotron angular velocity is given by omega c equal to minus q bz by m. And therefore, the acceleration of the motion will be given in a component-wise form as dvx dt equal to the minus of omega c vy and dvy dt equal to qm ey plus omega c vx and dvz dt equal to 0. That is the particle cannot be moving in the direction of the field, it cannot, of the magnetic field, it just be made to rotate. So since the particle has no initial velocity in the z direction, then we can see that Vz is equal to 0. So thus, particle motion will start at 0, 0, 0, that is at the origin, with z remaining 0 at all points along its path. And we therefore have that d2 vy dt square is equal to omega c dvx dt, and this we can see can be equated to minus omega c squared and the y component of the velocity. And or in other words, we can get a solution for the component of the y component in that form, and we use the initial value condition, that is vy must be 0 at the point of let's say for example at the origin at t equal to 0, vy is equal to 0, and therefore it means that the cosine value here must go to 0 for us to have that equation valid. So C2 is equal to 0, and C1 now is an arbitrary constant which you can determine. And therefore, omega c multiplied by c, Vx is going to be given by the minus of q by m Ey plus omega c, C1 sine omega c of t. At t equal to 0, of course, we know that Vx is equal to V0, and therefore we can get a value for C1, and we see that that's going to be given by that value, which is equal to V0 minus Ey divided by Bz. So the particle velocity at any time t will therefore be given by this equation, where we put the value there, and the Vy is going to be given by that equation. So we have two components. There is no z component because of how we defined the velocity of our particle initially. So the position of the particle is therefore going to be given by the derivative by the integral of that velocity. Okay, and we see component-wise, the x will be given by that equation and y component by that equation there. And with y equal to 0 at t equal to 0, then y can be given as that equation where we have put the C3 equal to 0 for that particular case. Okay, equal to, when you put that y equal to 0, you can get the value of the C3, and then you can obtain the values of y appropriately. So if the particle started from rest, the equations for x and y are then the parametric equations for a cycloid with time as a parameter. A cycloid is something that moves, when you have, say for example, a piece of paper attached to the wheel of a car, and then you try to follow the point of where the path of the paper as the wheel is rolling, it will form something like loops going down along the road, so to speak. It will be circulating. So that's what is called a cycloid. So a cycloid is the path traced by a point on the rim of a rolling wheel, and the trajectories of the particle will then be called trachoids. So there is a focusing effect of the fixed points on the x-axis given by the condition cos omega c of t equal to unity, or cos omega t equal to 2n pi. And the focal points are thus given by x equal to that in terms of y. Okay? And the time of flight between two focal points is independent of the initial velocity of the particle. This is also used, of course, in focusing of the electrons in electron beam in a wide angle cathode ray tube. such as the former tubes used for TV and the likes. That's why we used to use a magnetic coil. So the condition of V naught equal to EY by VZ will represent a straight line trajectory, and therefore properties of closed field trajectories will be useful in design of traveling wave magnetrons. Magnetrons are used in microwave ovens and also microwave systems, okay, communication systems, or you want to have a microwave photomultiplier, that is a multiplier for light, so to speak, using microwaves. So we note that if the particle is injected with an initial velocity V naught n equal to EY by Vz, the particle will continue along a straight path at this velocity with Vy equal to 0. And the electric force Q of Ey is then just cancelled by the y-directed magnetic force Q exbz. So if the initial velocity is different from that, magnetic force is, of course, the sum of that and a term that is given by that. And the first term will cancel the effect of the electric field, and the second term will yield the characteristic circular motion of the particle of angular velocity omega c equal to minus q bz by m, and the radius that will be given by that equation. So, and therefore particle motion in a closed field will be the sum of a straight line motion along the x-axis at the initial velocity and the circular motion imparted by the magnetic force. So, an important device that uses some of these results is what we call a space charge limited diode. When the charge density is high, the field that is acting on any one particle will be modified by the presence of the other particles. We know that like charges will repel, and therefore we have a field that will be different when the particles are close together. So the equation of motion must therefore be solved simultaneously with the Maxwell's equations, and we subject these to the appropriate boundary conditions that the fields must fulfill in that particular situation. So we consider a parallel plate diode, okay, where it's planar. We have an anode at a position D and a cathode at a position that position there, which we are calling 0. And we know that because of the charged particles, they are moving with a velocity v, and therefore the being charged, they'll represent a current density J, and the E field between the anode and the cathode is E, and is directed there. So we assume that the electrons are emitted from the cathode with 0 initial velocity. And therefore, at any position x, we have that the kinetic energy of the particle is equal to the local potential energy. So the equation of motion, okay, and E equal to the gradient of phi have been used for this particular case because we are dealing with a static field, so to speak. So the current density of the electron flux is therefore going to be given by J equal to rho v, which is Qn multiplied by the velocity v. So Maxwell's equations are implicitly involved when we are looking at the Poisson's equation for static fields in the following form. That is, the Laplacian of phi is equal to the minus of the volume charge density or free charge density divided by the permittivity. And the continuity equation, which shows that the curl or the divergence of J is equal to 0 for static fields, and therefore d rho dt, or the time rate of change of the free charge density, is also going to be equal to 0. So for a rectangular box, that is, we'll make a box between here, that is, we'll cut a box here along that which is what we'll call a Gaussian volume, and then we try to solve the problem. So for a rectangular box with a surface area S that is defined between the anode and the cathode of the diode, the integral form of the continuity equation may be expressed as the closed surface integral of J out of the ds, or out of the surface, is going to be equal to 0. This just means that the current that is entering the box through the left face will be equal to that is leaving through the right face. That is, there's no along the side walls. And this therefore requires that the current density be uniform everywhere between the two electrodes. So we therefore can write that J of X, that J at any position X is just going to be equal to a constant value J naught. So hence, when we recast the Poisson's equation in the form d2 dx squared of phi is equal to minus J naught over epsilon V, we can see that can be written as J naught over epsilon V into the root of m by minus 2q phi, and we can take this as a constant k divided by the square root of pi, where k is of course given by that equation for the one-dimensional diode. And we note, now we'll use tricks and see that the second derivative, or the derivative of d phi dx squared, is the same as 2 d phi dx multiplied by the d2 phi dx squared. That is the second derivative. And there, and d dx over the square root of phi is the same as a half, okay, of 1 by root phi d phi dx. And we are going to use this relation to simplify our equation as follows. So the Poisson's equation will be solved more easily when we multiply it through by the term d phi dx, and we'll get a d dx of d phi dx all squared equal to 4k d dx of the root of phi there. And when we integrate, we therefore get that the d phi dx squared is going to be given by 4k, the square root of phi as a constant of integration. So to get C1, we consider the effect of the space charge on the potential gradient. And the potential profile between the, the electrodes is shown here, where we have that line, where we have a linear line, and we have the third and a more curved line, which is the 3 and the 2. And we want to see what these lines refer to. So curve 1 is a straight line that will be obtained in the absence of charge between the electrodes. That is, if we were to integrate the electric field between the diodes, we'll get the same value, or that is, we'll get a constant increase in potential, okay, at from the cathode to the anode. The potential will be increasing linearly. Now, curve 2 will be explained by the by the expulsion of the electrons near the cathode and the acceleration of the electrons near the anode. That is, if we have any electrons near the cathode, okay, there will be a repulsion. And as they approach the anode, they will be attracted more easily or more quickly by the anode voltage. And therefore, the potential gradient will decrease in the vicinity of the cathode and will increase near the anode. The curve 3 is what we call the limiting case, when the negative charge density is very high. That is, the anode voltage is not sufficient to extract all the electrons from the cathode quickly. It's more like when you are trying to use a pressure cooker to cook, and you are trying to boil water and you are covering the sufuria, so to speak. Then the vapor pressure will be forcing the water molecules leaving the surface not to come out easily. It's more like you're putting a potential barrier, so to speak. And this is what is happening. And that's why we are calling it a space limited or space charge limited diode. So the potential gradient must therefore be equal to 0 at the cathode, and further change in the potential curve would produce a potential barrier near that cathode. This will only be overcome if the electrons leave the cathode with a sufficient a sufficient initial velocity. That is, they have an initial kinetic energy that will overcome the potential barrier. So the space charge limited boundary condition is therefore going to be given by d phi dx equal to 0 at x equal to 0. And in this case, C1 will be 0 and d phi dx is going to be given by those values. Or we get an equation of phi 3 by 4 equal to 3 by 2k square root of k multiplied by x. And since phi is V naught at the anode, then at the anode we can always write it as follows. And this is the equation that of curve 3. If we evaluate phi at the anode, then we'll see that J will be proportional to V naught raised to 3 by 2. And this equation is called the Charles-Langmuir law, or the 3/2 power law, that will be found in diodes or vacuum diodes. If you are dealing with a vacuum diode, that's what you get. And this is what we are going to be seeing, especially when we are dealing with electrodes or insulators between two electrodes, so to speak. So I think I can give you a 5-minute break because we are now at 15. Then we can meet in 5 minutes so that I can look at the plasma oscillations. So far, do we have any questions? So I'll assume that you are quiet, you are happy with me, and therefore you can take the 5-minute break. Let's meet after 5 minutes, that is at 10:21. So we'll now continue and look at what happens, or what we are calling the plasma oscillations. And if you recall what we said that a plasma is a substance that has equal number of positive and negative charges in equal concentration, such that the net charge density is equal to 0. So we can say that a plasma is an assembly of charged particles in which the time average charge density is equal to 0. That is, positively uncharged particles, negatively charged particles are present in equal concentrations on the average, and if they are assumed to carry the same charge of the charge of equal magnitude, so to speak. Now, the most elementary plasma motion would be an oscillation of an infinite slab, okay, plasma slab as shown below. That is, we are taking a slab and we see that we have positive on one side and negative on the other side, and we are looking at how they will be oscillating around there. So what we are going to say is that we'll displace the charges slightly to the right by a distance L plus Lx, that is that being x, at a distance Lx, and then release them. That is, release the forcing function, and see how the plasma relaxes back. So suppose that the positively and negatively charged particles are displaced from each other a sufficiently small distance x. If the slab thickness L is small, the time average field within the slab may be determined from as an electrostatic problem. So the excess charge on either side of the slab will constitute charge sheets, and if the charge density of the negatively charged particles is n, then the surface charge density on each side of the charge sheet is just going to be given by rho s equal to q multiplied by n and multiplied by the value of x, which is the displacement, where this is a surface charge. So the magnitude of the electric field intensity in the slab is from Gauss law going to be given by E equal to Q of n over epsilon naught and multiplied by x, where the E is of course the electric field intensity, and this is the charge density, and divided by the permittivity of the material and multiplied by the distance or the displacement x. And this states that for sufficiently small displacements, the restoring force acting on the slab will be proportional to the charge displacement. And this is just the condition that we require for a simple harmonic motion, which is an oscillation. So in a plasma in which the free charged carriers are generated through ionization of neutral molecules, then the positively charged particles will usually be ions, and therefore they will be of a much greater energy mass than the negatively charged particles, which are usually electrons. Okay, and therefore, because of the massive nature, the positive ions can be regarded to be relatively immobile when compared to electron motion, and therefore the plasma can be treated almost like a conductor, a solid conductor such as copper, where we just have the electrons permeating the lattice core ions that are immobile in the lattice position, so to speak. And if the electron and electron-neutron particle collision frequency is low, that is, then the equation of motion for electrons is going to be given by m of the second law of motion, that is m times acceleration, equal to the value of the electric field force that is acting on those particles, so to speak. And therefore, the equation of motion describes oscillations at a fixed frequency omega p, given by omega p equal to q times the square root of n divided by n epsilon naught. And omega p is therefore referred to as the plasma frequency, okay, and is a characteristic of that plasma. And therefore, d2x dx, the t squared, or the acceleration, is going to be given by the minus of omega p squared multiplied by x. This has a general solution of the form x given by a positive component where it's varying as a minus of j omega pt and the conjugate value. And this is the phasor displacement for the free oscillations of the plasma slab and can only occur at the plasma frequency. That is, that displacement is occurring only at the plasma frequency. So oscillations at other frequencies will of course be possible if the plasma is then driven by an external oscillating field. An example would be an electromagnetic wave that will be propagating through that plasma, just like what we said before. Say, for example, a communication signal leaving the IS, or the International Space Center, coming down space station and being beamed down to Earth. It must pass through the ionosphere. So we assume the plasma consists of electrons and singly charged ions of a much larger mass, such that they are relatively immobile with respect to the electrons. So that we combine Maxwell's equations with the equation of motion for the electrons, and we analyze the possible oscillations that the plasma can undergo. So electron motion will enters into the Maxwell's equation through the current and the charge densities as follows. The current density, J of t, will be given by the charge density multiplied by the velocity of the charge particles. And the free charge density is going to be given by that equation Q V of N T. So N of t and V of t are the time-dependent electron concentration and average velocity, respectively. So we'll assume low amplitude harmonic time-dependent electron oscillations. That is, the displacements are not very high, are not very large, and therefore we can express delta, the N of t and the V of t, to be of the form N0, that is an average value, a time average value, plus the real part of the time-dependent changes in the electron concentration, and the V would be given the same way. And therefore, N0 is the time average electron concentration, and the electrons will be assumed to have zero average velocity, and that's why we don't have a V0 adding to a change value. So for the low amplitude oscillations assumed, the current density is therefore going to be given by J of t equal to Q N0 and the real part of the velocity. And since if we were to take the delta N of t multiplied by V of t, it would be approximately 0, because we are talking about very small changes. So the relatively immobile positive ions make contributions or negligible contribution to the total current density in Ampere's circuit law, and significant contribution to the steady state charge density, however. And this contribution will be cancelled by the steady state electron charge density in Gauss' law, and therefore that can be removed. And therefore, no steady state fields are established within the plasma. So with N, V expressed as phasor quantities, we can then express Maxwell's equations in a form of the following form here. That Q multiplied by E is equal to J omega, Jm omega, and multiplied by V itself there. And the curl of H is of course going to be given by the displacement current density plus the conduction current or the convection current that we have there. And the curl of H of E is going to be given by the minus of the J omega mu, or the time rate of change of the magnetic field intensity. And we know that the divergence of E is of course going to be given by the charge, volume charge density divided by epsilon r, and we know, as usual, the divergence of the magnetic field intensity is going to be identically 0, since we don't have magnetic charges in it anywhere. So the continuity equation is contained in the Ampere circuit law and in the divergence of E, and will take the form that the divergence of that velocity is the same as the j omega multiplied by n. So while these equations can be solved directly for the fields, we may get a major simplification if we first substitute the equation of motion into the Maxwell's equations themselves. So we know that the V is given by Q by j omega m and multiplied by the E, and therefore we can use, for where we have V in the Maxwell's equations, we replace it by this equation here. We get better values, so to speak, or at least simpler expressions. And therefore, in Ampere circuit law, you can have that is going to be given by that value here plus Q squared n by that, where we have replaced the V with the E itself, and we get a value that j omega epsilon naught into that equation there, multiplied by that. And if we look at this looks like an effective permittivity for the plasma when we compare with the usual Maxwell's equations, in which we have no conduction current. Would get that the curl of H is equal to j omega epsilon E, so to speak. And this is how it appears here as well. So this will therefore suggest a treatment of the plasma as a dielectric with an equivalent electric permittivity given by epsilon equals epsilon naught multiplied by that equation there, which we can write as epsilon naught into 1 minus omega p, or the plasma frequency divided by omega all squared. Omega would be the frequency of the external field that is passing through the plasma. So when we are looking at ionospheric studies, the relative permittivity is usually expressed in the form that the ratio is epsilon r equal to 1 minus x, where x in this particular case is just omega p by omega all squared. Remember, this x is not the chi that we have always been using for epsilon r, but this is called the electric susceptibility. This is just a new variable that we are using to represent that ratio of the plasma frequency to the frequency of the field. And therefore, when we look at the divergence of E, we can get that equation, or you can write it as shown there, when we take these values here as relatively independent of space. Okay, that is the gradient of Qm j omega m equal to 0, where we are assuming that the density of the electrons does not change much with space. And now, the divergence of E is therefore going to be given by Qn by epsilon naught, and therefore n can be given in terms of the divergence of E, and we can therefore put all those values in there, and we get an equation of that nature, where that the divergence of E multiplied by that is equal to 0. And this can be expressed in the form that the divergence of epsilon multiplied by E is equal to 0. And this expression is therefore consistent with the idea that the plasma can be represented by an equivalent permittivity. So one advantage of this is that we can use the existing solutions for wave propagation in a dielectric, okay, even at lossy dielectric, in the study of wave propagation through the plasmas. And it will make our life easy when we are dealing with communication through the ionosphere, so to speak. For example, if we consider a Y-polarized uniform plane wave that is propagating in the positive Z direction in an unbounded plasma, then the electric field intensity will be a solution of the homogeneous Helmholtz equation, where is d2 ey and dz squared plus omega squared mu epsilon ey equal to 0. And this has a general solution that we have already found that it's a a wave component propagating in the positive z direction and a negative component that's propagating in the minus z direction. And this can be expressed in the following form, that we can always express this as a square root, that is jk naught into that value plus ak naught into that value, when we replace the value of epsilon with the value of epsilon that we have found in a few slides above. K naught, of course, is the usual lossless propagation constant given as the square root of omega squared mu naught to epsilon naught. And therefore, this illustrates the similarity of the wave propagation through a plasma to the propagation through an ordinary directly when x is less than 1, that is for omega p less than omega. That is, if we are the frequency of the field is higher than the plasma frequency, then it would follow this kind of value here. That is, this equation here will be imaginary, okay? It will be imaginary, and therefore we can always just get minus jk naught multiplied by z, or multiplied by a small positive value multiplied by z. But in case x is larger than unity, then we'll have that this will become a real value and we have attenuation. And therefore, what we call this wave that is being attenuated as it goes through the plasma will be called an evanescent wave. We shall see that we said that before, that when you drive the plasma at below the plasma frequency, we have cutoff condition, okay? So by analogy to waveguides, omega p is therefore equivalent to a cutoff frequency for the plasma. And the wave that is incident on the cutoff plasma from free space will just be reflected back into free space. If we are sending the wave from down below Earth, it will be sent back towards Earth again. And this type of reflection is the reason why radio waves will bounce off the ionosphere and allows for long distance radio communication around the globe. Since electrons frequently collide with the gas molecules, the ions and among themselves as well within the plasma, there will be a non-zero power loss. And the collisional losses will lead to an attenuation of the propagating wave at frequencies above omega p. It will lead to partial reflection of the propagating waves at frequencies below omega p. And therefore, we look at an example of that, and we look at the collisional effects in a plasma may be accounted for by including a frictional force term in the equation of motion as minus m theta and v, where theta is the electron collisional frequency, how many times the electron is colliding per unit time with other particles. So, show that the concept of plasma permittivity is valid with the collision effects included, hence show that the relative permittivity can be expressed in the form epsilon r equal to 1 minus x by mu by u, where u is defined as 1 minus jz and z given as the collisional frequency of the electron divided by the frequency of the field. So, what the equation of motion is, of course, going to be written in that form, where we have the what we call the damping effect, and then we add the values of those equations, that is the expressions, and we can see that E can be expressed in terms of j into 1 minus jz, and thus v is going to be given by that, and the curl of h just going to give you that equation there once you do the simplifications. So the electron density N is very high in a metal, and hence the frequency of collisions with the lattice core ions at room temperature would be very high. And this therefore leads to that phenomenon that we know so well and we call electrical resistance. So at temperatures near absolute zero, some of the metals, of course, exhibit a complete loss of resistance, what we call superconductivity. If the electrons in a superconductor are assumed to move freely without collisions, then a simple theory of conductivity may be formulated, and with N very high, the plasma will be in cutoff and the waves will penetrate only short distances into the network. So if we viewed a superconductor as a cutoff plasma, okay, then we can provide a coarse view of its ability to expel electromagnetic or the magnetic fields from it. That is, a superconductor cannot support magnetic fields in itself. So a wave entering the superconductor would be attenuated with thin a skin depth that is given by delta S equal to 1 over k naught x minus 1 when n is large. Or in other words, the depth of penetration is just n by that. Remember, a superconductor is different from a perfect conductor in the sense that a perfect conductor can have a static magnetic field within it. A superconductor will not have any magnetic field of any kind. The electric field and the magnetic field will be both zero inside a superconductor. That's something you have to understand that. So this states that for a high electron density, the skin depth is therefore independent of frequency, which is opposite to that we had for a perfect conductor, where we saw that the skin depth is proportional to the square root of frequency. So a superconductor will hence tend to exclude magnetic fields, even if these fields were applied very, very slowly. So perfect dielectric materials, okay? Now, I think with this now we are looking at polarization of the dielectric materials, and therefore I'll just introduce so that next week we can be looking at the gaseous, we can finish what we'll have left today and we look at the gaseous materials. I know today we have given quite a lot of material to think about over the weekend. So I'll just introduce as follows, that the perfect dielectric material, we don't have any free charges in them. That is what we must remember. Free charge are in the form of the, say for example, the conduction electrons that we have in metals. They don't appear in dielectrics. All electrons are bound in the bonds forming the solids or forming the material itself. So if we were to apply a steady external electric field, okay, we can cause slight but significant displacement in the centers of mass of the bound charge distributions relative to each other. That is the nuclear positive charge and the electron cloud around a neutron atom or molecule can be displaced and therefore elongated in the direction of the field. So each infinitesimal element of volume of the dielectric will therefore behave like an electric dipole. And the induced dipole field will tend to oppose that applied field that we are applying on the dielectric. So a material in which the charge distribution distortions exist is therefore said to be polarized. It's in a polarized condition. This is different from the wave polarization because we say that wave polarization, we are just describing the vector or the electric field intensity vector in a wave as time progresses at a fixed point in space. Now here we are talking about material polarization, where the charge distribution on the molecules forming the material are displaced from each other such that we have an induced electric dipole. So most materials will exhibit polarization only in the presence of an applied field. If you remove the field, they will relax back to their neutral conditions. A few called the ferroelectrics, okay, will have permanent polarization. That is, they are already polarized in themselves. And this usually happens, especially when the molecules are formed between atoms with different electronegativities. And therefore, the electrons forming the bonds will be more prevalent or will be found near one of the molecule of the constituent atom than the others. Say, for example, the water molecule H2O. The electrons, the shared electrons in the bonds surround the larger or the more electronegative atom, oxygen, and therefore oxygen acquires a negative charge, while the hydrogen acquires a positive charge, and therefore that forms an electric dipole. And it's because of this electric dipole that we have liquid water at room temperature. So ferroelectric crystals then exhibit spontaneous and permanent polarizations. And electrics are materials that become permanently polarized when allowed to solidify from the melt in a strong electric field. That is, you'll melt the material, then apply a strong electric field, then allow the material to cool down, and therefore the molecules will be, since the molecules are polarized and they'll be aligned with a strong field, then as they solidify into place, they'll keep their orientation, and therefore the material already contains whatever polarization of some sort. These electrodes are used in applications such as making microphones and so forth, high quality microphones and so forth. So the displacement of the center of mass of the negative electron cloud relative to the nucleus of the atom, we call it electronic polarization, because it's the electrons that are being moved. If we look at the molecular scale, we have what we call ionic and orientational polarization, which becomes important. So ionic polarization will result from the displacement of positive and negative ions in ionic molecules. That is, if you have ionic molecules, okay, we can get the molecules trying, the positive side of the molecule trying to align itself with the field, and therefore we have an orientational polarization as well. Okay, so the orientational polarization will arise when we have materials with permanent polarized molecules as well. So the randomly oriented polar molecules will align with the externally applied field, and we have, therefore, at the macroscopic level, we can have that space polarization, space charge polarization, which would appear when we have charged particles accumulating along potential barriers, such as grains. Say, for example, polycrystalline materials, that is, materials with formed of very many different types of crystallites. They'll form boundaries where impurities could accumulate, and this, if they are charged, will be a potential accumulation of charged particles, and will introduce polarization in the material. So application of an electric field will cause the electrons to pile up against the barriers, and will establish a charge separation and therefore an electric dipole. So we have, what we need to know is that in materials, we have one, electronic polarization, that is displacement of the molecular charge cloud. Two, we have the ionic polarization, and we have the orientational polarization if the molecule is already polarized and it aligns itself with the applied field. And we also have what we call the space charge polarization, where we have charge accumulation of boundaries or grain boundaries. But all these four types will be indistinguishable when we are dealing with static fields. But if we were to apply a dynamic field, then they all react to the field with different time constants, and therefore we'll expect them to have resonances that are slightly different from each other. And this is what we shall be looking at when we look at the values of those, that is the polarization of the dielectric materials. And I now suggest that I stop here so that we can deal with this next week when we meet on Wednesday. Okay, so we'll look, all we can say is that to a first order, the atom will be modeled as a nuclear positive point charge surrounded by a spherical electronic charge cloud of uniform charge. And with this one now, we are going to be using this model to discuss electronic polarization, okay? And we shall use the knowledge we get from electronic polarization to generalize for the other three remaining polarizations that are possible in electric materials. So with that, I wish you a nice weekend. In case you have any question, you can raise them up now. There's a suggestion here. What is this suggestion about? Let me see. The comment was about what? The splitting of the 2-hour lecture into what? 1 hour lecture and 1 hour tutorial for the material covered. Now, even when I've given you the whatever the material to read first before ahead of me, but someone is complaining I'm going too fast. I tried to see how I can reduce that speed. We have the 2-hour session to 1 hour lecture, 1 hour tutorial for the material covered. That one is, well, we could use the Wednesday lessons to be the tutorial. But first of all, I want to cover the dielectrics of the insulating materials before I can do this. Right now, I don't know how much time I have. The CAT, I understand you guys will be going for, you will be having a lab session sometime. When is your lab session?
January 10th to 21st.
So maybe that's when, since they are asking us to give face-to-face CATs during the lab sessions, you know, at the lab week when you will be in the university. So I'll suggest that's the time we'll have to sit our whatever our CAT. Is that okay?
Yes.
Yeah, because it's what they have told us is that the CATs have to be, or the exams have to be face-to-face. So we'll have to wait until you guys are in the university, then you can sit the CAT there. But like I said, electrodynamics, if you have already followed, if you have looked at it, you can see that we are just talking about the same things. That is the Maxwell's equations, the boundary conditions, full stop. There's nothing else we are talking about. The only other thing you need is some knowledge in vector calculus, and you are done. All these things we are talking about, they all reduce to the same thing. It will just always reduce to the Maxwell's equations and the boundary conditions. Okay?
Yes.
You get it?
Yes.
So I'll the split of the session, I'm going to request that I do that after I'm through with the insulating materials, okay, which I'm sure we can cover them in just a few lessons, because mainly it's just bubbling around. There's not much calculations, except some calculations for, you know, gas discharge and so forth, which is easy to follow. So once we are through with that, we'll be able to do the rest of the value, or the rest of the lessons can be used for tutorials. Okay.
Yes.
Agreed.
Yes.
So okay, if you notice from the material I've sent, there are other material that belong really to the what we call the appendix. They are put there for completeness. We won't be requiring you to follow the material, just for your further reading, just to see, because like I've said, we are just repeating these things all along. Boundary condition, Maxwell's equations, boundary condition, Maxwell's equations every time. And therefore, those ones are just giving you other aspects of it. And some are just like vector calculus, which you can look at. And if I haven't sent that, I may be sharing it in a few, by next week I'll have shared it in the Google Drive. So with that, then I wish you a nice weekend. Let's meet next week then. So since I don't have any further ado, I'll just stop the recording.